So, ladies and gentlemen, dear colleagues, welcome. My name is Dean Hanzalek, and you are watching the 68th talk of the scheduling seminar. Today, I'm happy to introduce Thomas Lidbetter from Management Science and Information Systems Department in Rutgers Business School in New Jersey. He received his PhD in 2013 on Surge Games with Steve Alpern. Currently, he is associate professor of the same department, and he is working on search, on games, discrete optimization, and scheduling problems. As far as for hobbies, he is interested in climbing and cycling, and he also plays piano. So, Thomas, it is great to have you here, and please go ahead.
Thank you, and thanks very much to Zdenek and to Alessandro for inviting me to talk in this series. So let me share my slides. I hope you can all see that okay. This is joint work with a few authors because it covers a couple of different papers. So Robbert Fokkink, Felix Happach, Lisa Hellerstein, and László Végh. So let me first just briefly say what I'm going to talk about. So I'm going to introduce a general problem, which I'm going to call a min-sum ordering problem. So it's a family of problems, really. And then I'm going to talk about it, a kind of subclass of this min-sum ordering problem. So I'll talk about two main subclasses. The first one will be relevant to this paper on submodular search and machine scheduling from 2019. And the other one, so it'll be two approximations for a subclass of these problems. And then I'll talk about another subclass of problems, and I'll give a 4 alpha approximation. And I'm going to say what alpha is at some later point. But that's based on this work here from Inform's Journal on Computing. So this work is not very recent work, and I haven't been working on scheduling super recently. So it's slightly older work, but these two papers kind of come together they're both relevant to min-sum ordering problems. So it made sense to talk about them both at the same time. So let me start. Before I tell you what the min-sum ordering problem is, I want to give you a very classic, easy scheduling problem, which I'm sure everyone's heard of. So you have n jobs that must be scheduled. Each job has a weight. So these are the WIs. Here the weights all add up to 1. That isn't necessary, but I'll explain in a second why I've made it so they all add up to 1. There could be any positive number. And the processing times are PI, so this is the time it takes to process each of the jobs. And the problem is we want to schedule the jobs in some order to minimize the sum of weighted completion times. So this notation here means we have one machine that's processing the jobs, so we just have to choose between the 5 factorial different orderings of the jobs. And the objective function is this part here, the sum of the WI times the CI, where CI is the completion time of job I. So this is actually dependent on the ordering. So the notation is misleading. There should be a dependence on the ordering in this CI, but for a given ordering, CI is the sum of all the processing times of all the jobs up to and including job I in that particular ordering. So intuitively, jobs that have a higher weight, so they're kind of more important, so you want to schedule sooner. But then again, if they have a high processing time, you might not want to put them so soon. So it turns out the solution to this problem is there's a very simple index solution. You want to perform the jobs in non-increasing order of this index, wi over pi. So you want to start off with jobs that maximize the ratio of wait to processing times, which you can view as a kind of density. So you want to maximize the wait per unit processing time. This goes back to a paper of Smith in 1956, and this rule is called Smith's rule. You can also view this as a search problem, which is how I got interested in scheduling through search. So if you imagine these, rather than scheduling n jobs, you have a target that's hidden in one of n locations, and the pi is the time it takes to search each location. The wi is the probability that the target is in location I. Then you could be interested in ordering the locations, so choosing what order to search the locations to minimize the expected time to find the target. And that's an exactly equivalent, identical problem to this. And so you can find in the literature that this search problem is solved almost the same time as the scheduling problem in a different paper. Or I think actually that problem appears in the dynamic programming textbook of Bellman. Okay, so let me now write this problem in a slightly different form. So say we have a particular schedule, a particular ordering of the jobs. I'm going to write Sj as the set of jobs up to and including job j for this particular schedule. So again, this, as with the notation for the completion times, this has a dependency on the ordering of the jobs, which is suppressed in the notation. But for a particular ordering, Sj is all the jobs up to including job j. Then I can write the sum of completion times, the sum of wj, cj, in this slightly strange way, using two set functions. So one is f. So f of a set of jobs here is just the sum of all the processing times of those jobs. And g of a set of jobs is the sum of all the weights of the jobs. So that the jth term in the sum is f of Sj, the sum of all the processing times of all the jobs up to and including job j, and which is the same as Cj. And then this difference here, g of Sj minus g of Sj minus j, so all the jobs up to job j except for job j, this is just pj. So it's a kind of weird way of writing pj. So these functions are both non-decreasing in the sense, so non-decreasing with respect to subset with respect to inclusion. So if I add an element to the set, f and g both increase because I'm assuming that pj and the wj are non-negative, and they're both modular as well. Where modular means that f of a set S is just the sum over all the elements of S of f of those elements, and the same for g. So it's a very particular type of, they're both very particular types of set functions. So this motivates a more general problem, which is that we have a finite set V of cardinality n. So think of V as the set of jobs. And we have an arbitrary non-decreasing cost function f from subsets of jobs. So this is all the subsets of V, and it's a real valued function. And we could, I think for all the applications I'm talking about, f is positive as well. So you can imagine the range of f is just positive real numbers. And we're always going to assume f of the empty set is 0. And then we also have a non-decreasing weight function g, again defined on subsets of V, and g of the empty set is 0. And the problem is we want to choose a chain, so a chain of subsets of jobs that increases one by one So S0 is the empty set, S1 just contains one job, S2 contains two jobs, and so on until we get all the jobs, V. And we want to minimize this sum. So this kind of weighted sum of costs. And you can picture this as a histogram or bar chart like this. So if I put G on the x-axis and F on the y-axis, then the jth term is the area of this bar. So it has height F of Sj and width G of Sj minus G of Sj minus 1. So this isn't quite the problem, the min-sum ordering problem. I'm going to define a problem that's a little bit more general than this on the next slide. So this is the difference. So the red things are the difference here. So the min-sum ordering problem is almost the same, but I'm going to allow any chain of subsets of jobs. So it doesn't have to be that the jth element of the chain has j members. So you could skip jobs. So you can have an arbitrary number k of subsets in the chain. It's easy to see that if you allow this extra freedom, then that doesn't actually help you, because there will always be an optimal solution to this problem that is a chain that just increases one by one. Because if you skip elements of the chain, then that's just like combining two of these bars into one big bar like this. So this doesn't actually help you, but by defining the problem in a more general way, it's just easier to analyze approximate solutions. So we're allowing this more general definition. Okay, so now let's go back to scheduling, and I'll give a harder scheduling problem based on the original scheduling problem I showed you. Also, probably familiar to many people. So now suppose we want to schedule some jobs, but there are precedence constraints given by a DAG, directed acyclic graph. So the interpretation of the precedence constraints is, if I have a job, say this job here, this job cannot be completed until it can't be processed until all its predecessors have also been processed. So this has, my cursor's disappeared. There we go. This has two predecessors, this one and this one. So we cannot process this job until these two jobs have both been processed. So that means not all orderings are feasible. Here's an example of a feasible ordering. We could start with this job. This has no predecessors, so that can be processed at any time. So after that one, we could, the possible next jobs are this one here or this one here. So let's do this one. After this, the only possible job we can process next is this one, because these two, for instance, can't be processed because not all of their predecessors have been processed yet. So we have to do this one next. And then the only possibility next is this one, has both of its predecessors already processed. Then we can process this one. And at this point, any ordering of the remaining jobs is feasible. So let's say do this. So again, we want to minimize the sum of weighted completion times. And in scheduling notation, this is how this problem is usually notated. So again, one machine. So you can also define these problems with multiple machines, which is not relevant to this talk. The press here indicates precedence constraints, and again we have the same objective function, weighted sum of completion times. So Sidney showed in 1975 that an optimal schedule must begin with a closed subdag that maximizes this ratio. So this is like a version of Smith's rule. Remember, Smith's rule just orders all the jobs such in decreasing order of the index of weight to processing time. So this is like a generalization of that rule. We take a closed subdag. Closed means that if a job is in the subdag, then all its predecessors are also in the subdag. and we want to maximize the ratio of the total weight of all the jobs in that subdag to the total processing times of all the jobs. Um, and a closed subdag that maximizes this ratio can be found in polynomial time. There are different ways to do it, but you can reduce it to a maximal flow problem, and it can be done very quickly. So this gives rise to a so-called Sidney decomposition of the jobs. So once you've found this subdag that maximizes this ratio, the theorem says you have to start with these jobs in some order. We don't know what order. The theorem doesn't tell you what order the jobs should be processed in. But then after they've been processed, we can look at the remaining unprocessed jobs and repeat the same process. So find the subdag that maximizes the ratio of weight to completion to processing time of the remaining jobs and continue like that. So you get a decomposition of the jobs into this ordered partition. So the theorem says that jobs should respect that decomposition, the order of the jobs. Now, if the precedence constraints are tree-like, so if this DAG is a tree, or even more generally, if it's a series parallel graph, then you can show that the problem can be solved in polynomial time. So if you find this subdag of that maximizes this ratio, then that actually gives you a unique optimal schedule. So later on, this problem is shown to be NP hard. And there are many two approximations for this problem, where a two approximation of a problem of a minimization problem in general is a solution whose objective function is at most twice the objective function of an optimal solution. So I'll talk a lot about approximations for problems in this talk. So there are a whole host of approximations here, and in particular, there are two here from Chakuri Motwani and Margot Kairan and Wang, who showed that any schedule that's consistent with a Sidney decomposition is a two approximation. So if I find a Sidney decomposition, as I described in the previous slide, and I choose any schedule that's consistent with that decomposition, that will be a two approximation. And then Correa and Schultz showed that virtually all known two approximations are consistent with some Sidney decomposition. So I want to write this scheduling problem in the form that I described before as a special case of the min-sum ordering problem. So if this, we want to write it in this form by choosing an appropriate f and g. So this time we're going to choose G to be the same thing again, the weight of all jobs in a subset S, G of S. And then F of S, this time will be the time to process all jobs in the precedence closure of S for a subset S of jobs. And by a precedence closure, I mean if you take, for example, these two jobs in my DAG, the precedence closure is all the jobs you need to do in order to process these jobs. So all the predecessors and the predecessors of the predecessors, etc., of all the jobs in S. So that would be the precedence closure of S. So in that case, I claim that the problem of minimizing this is equivalent to the problem of minimizing the way to completion time with precedence constraints. So I claim that using these set functions, any optimal ordering must respect the precedence constraints. And this is because an optimal ordering would never want to skip jobs. So even though we're allowing any permutation of jobs here, you would never want to skip jobs, because if I skipped, say, from this job to this job, then I immediately have to pay all the processing time of everything in the precedence constraint, everything in the precedence closure of of this set of jobs that's already been completed. So I have to pay the processing time of the jobs that I skip if I skip jobs, and I don't get the benefit of the weight of those jobs until later on when those jobs appear in my ordering. So there'll be an optimal solution that respects the precedence closure, respects the precedence constraints. So now this time G is the same, so G is still a modular function, but this F is a submodular function. And the way to think about submodular functions is decreasing marginal costs. So think of it like a concave function. So I've put two equivalent definitions of submodularity here. And I think the first one is more intuitive. So the first one says, if I have a set A of jobs and then I add a set J that's not in A, then this thing on the left, this is the marginal cost of processing J after processing all the jobs in A. And then this is the same thing on the right-hand side, but with A prime, where A prime is a smaller set than A. I'll show you a picture of this in a second. So F being submodular says that if I've already done more jobs, then the marginal cost of processing job J gets smaller. And this is because if I've already done more jobs, then that may include jobs that are successors of J. So this thing on the left may be just 0. If, for instance, there's any job in A that which is a successor of J, because then in the precedence closure of A, that will include J. On the second line, this is an equivalent definition of submodularity, which is less intuitive to me, at least. And here's a picture, which is from the first definition. So there's A, and I've got job J. So the red bit is like the marginal cost of processing J. And then if I've got a smaller A prime, then the marginal cost should be bigger. So let me give you another more general scheduling problem. So rather than having weights on jobs, let's suppose we have weights on all subsets of jobs. And it could be that most of these weights are 0, but for every subset A of jobs, we have some weight WA. So for instance, we might, it could be something as simple as saying we have some number K and all subsets of size K have weight 1 and everything else has weight 0, something like that. And then instead of minimizing the sum of weighted completion times of jobs, we want to minimize the sum of weighted completion times of subsets of jobs. So you would write the objective function like this, and using the same style of notation, this is how you would denote it. And I think this problem actually makes a little more sense in a search setting. So if you think of the search version of the problem, so you have several targets, and there's a target hidden in a subset A of locations with probability WA, and the problem is now to find an ordering of the locations that minimizes the expected time to find all of the targets. And so that would be an equivalent problem. So in that case, we can still write this as a special case of the min-sum ordering problem, where this time we change G. So F of a subset is still the processing times of all the jobs in the precedence closure of that subset. And G of the subset is now, rather than the sum of all the weights of the subset, it's now the sum of all weights of all subsets of A. So then I claim that this is that the objective function can be written in this form. As before, F is submodular, and G is now supermodular, which is the complementary property to submodularity. So the same definition, but with this inequality sign reversed. So it's increasing marginal benefit. And this is because this quantity now represents the weight of all the subsets that get added in once you've processed job J. So all the subsets of A union J, there's not subsets of A. And if I take a smaller set, A prime, then adding J kind of releases a larger number of subsets. I'm just worried now that I have this the wrong way around. So this is less than or equal to, so that's actually, yeah, apologies for that. That should actually be greater than or equal to. So if you've already done processed more jobs, then adding an extra job J, that releases, that should release more subsets of jobs that include J. So that should be the other way around there. Okay, so this new scheduling problem, or the one not new when we defined it in our paper, is another special case of this min-sum ordering problem, with F being submodular and G being supermodular. So the topic of the first paper is to try and solve this problem, min-sum ordering problem, with F being submodular and G being supermodular. And actually, we didn't realize when we started writing the paper that this exact problem had been considered in an older paper by Pisarouk from 92, who showed that for this choice of F and G, this class of functions F and G, then any solution consistent with a Sidney decomposition is a 2 approximation. And a Sidney decomposition can be found in polynomial time. And what I mean by a Sidney decomposition in this context is a decomposition that you can get by, remember in the original scheduling problem with precedence constraints, you get the decomposition by finding a subset that maximizes the ratio of weight to processing time. So that in this context, we find a subset that maximizes the ratio of the weight function to the cost function. So maximizes G of S, the ratio of G of S and F of S. And by repeating that maximization, you can get something that's like a Sidney decomposition. So this is like an equivalent to the 2 approximation results for scheduling with precedence constraints, single machine scheduling. Let me give some idea of how Pisarouk proved this. So this is a picture of a solution, a feasible solution to this problem. So I'm putting F on the, I think this is the opposite way around. I drew the histogram before, but now F is on the x-axis and G is on the y-axis. Suppose I have some possible chain of jobs, then the objective function is represented by the area of these red rectangles. So this is the objective function. That's the thing we want to minimize. So Pisarouk said, let's minimize something slightly different. Let's minimize this blue area. So the sum of all the areas of these trapezia, which is represented by this expression here. And he observed that if you can solve this problem, then this will be a 2 approximation for the original problem. And that's because this cost C prime it's certainly less than, so C prime of S is certainly less than C of S, but it's also at least half of C of S. Because in each of these rectangles, the blue bit is at least half the area of the total rectangle. So if you can solve the problem of minimizing this expression, the C prime of S, then that gives you a 2 approximation. so how do we minimize that? Well, it's pretty clear if all these blobs represent all the jobs, all the subsets of jobs rather. And so for each job, this represents f of that subset. The x coordinate is f of that subset, and the g coordinate is g of that subset. Then to minimize the to minimize the c prime, we can take the upper envelope of all these points, and if these points define a chain, then that must be optimal because it will minimize this blue area. So Pizaruk showed that these subsets do in fact define a chain. So that's the meat of the proof. And so that gives a solution to minimizing C prime, which is therefore a 2 approximation for the problem of minimizing C. And this is a Sidney decomposition because this point here, this is clearly the subset that maximizes the ratio of G to F. And then once that's been chosen out of the remaining jobs, this is the one that maximizes the subset of G to F and so on. So how do we maximize that? How do we find this upper envelope? Well, if you maximize this is so assuming that G of all of the jobs and F of all the jobs is equal to 1, then if we maximize this quantity G of A minus F of A, this will find some subset on that upper envelope, and then we can decompose the problem into finding the upper envelope of this and finding the upper envelope of this. So you just have to do at most n minimizations like that in order to find this upper envelope, and or maximizations, and this is maximizing the sum of a supermodular function and the negative of a submodular function, which is also a supermodular function. And if you add two supermodular functions, you get a supermodular function. So this is maximizing a supermodular function, and it's well known that this can be done in polynomial time. So that's how the upper envelope is found. Now let me tell you our result, which is that it's a little stronger than what Pizaruk showed. So basically, we find that that if you take a Sidney decomposition, so you find something of maximum density, then the optimal search, any optimal search, must start with searching the elements of this subset of maximal density in some order, and then recursing. That's this. If you find the whole Sidney decomposition, the same thing is true. So any optimal search must respect Sidney decomposition. And the idea of the proof is a kind of switching argument, which is if you go back to the very first scheduling problem that I talked about, and Smith's rule, the way you prove Smith's rule is a switching a very simple switching argument. This is basically a more sophisticated version of that argument. So you start off with an optimal search. So this circle here represents all the possible jobs, and the red rectangle represents a subset of maximum density. So an optimal search must be of the following form. It starts with some subset of jobs B1, which could be empty, but B1 is disjoint from this subset of maximum density, and then it processes some jobs in the red subset, and then it processes some other jobs that aren't in the red subset, and so on until all the jobs in the red subset have been processed. So that's an arbitrary optimal strategy. We basically show that if you define another schedule as follows, that processes all the jobs in the red subset in the same order and then processes all the jobs in the blue subset, then that's better than the optimal strategy. So it follows sorry, I keep saying strategy because I'm thinking of game theory. I should say schedule. So this is better than the optimal schedule. So it implies that the optimal schedule must start with all these jobs in the red subset, maximum density. So in the picture here, this is the subset of maximum density. So what are the implications for scheduling? It means we get a 2 approximation for this more general problem of minimizing a weighted sum of subsets, weighted sum of completion times of subsets of jobs. And we could also look at this problem. So you could take subsets of jobs, or we could go back to I mean, this is a special case of just a weighted sum of jobs. So you can imagine this is just weighted sum of jobs, but we could apply a function to the completion times. And if that function is concave, then writing in terms of the min-sum ordering problem, the f is still submodular, because if you compose a concave real function with a submodular function, you still get a submodular set function. So this comes under the umbrella of our results, so you get a 2 approximation as well. Now this problem, as it turns out, was also, or the problem at least with a function of completion times with weights on single jobs. This was looked at by Schultz and Verchet, and they got an approximation in a slightly different way using the Sidney decomposition for this problem. So if you start off with this Sidney decomposition, and then anything that's consistent with that Sidney decomposition will also be a 2 approximation for this problem. Our Sidney decomposition is slightly different because we get a different f when you apply this concave function h. And in a sense, our Sidney decomposition, I think, is the correct one, because we have the result that any optimal strategy must be consistent with that Sidney decomposition, which is not true of the original Sidney decomposition for the new problem. So just to say briefly about functions of low curvature, so we can refine the approximation ratios slightly by using the concept of the curvature of a submodular function. So if you have a general set function f on n, okay, it was v before, but v equals n, then we can define this thing k like this, and to understand where this definition comes from, imagine that f is a modular function, first of all. So in that case, if f is modular, the top of this fraction is just equal to f of I, and so the fraction is 1, and so k is 0. So for modular functions, this is 0. If I have a submodular function such that adding I to everything else doesn't change f, then the top of this function is 0. And so the fraction is 0, and so k is 1. So for a submodular function, k will always be between 0 and 1. And the higher it is, the more submodular it is in some sense. So if k is 1, that means that there's some situation where adding I does nothing to f. So it's kind of very submodular. Now, if I take a supermodular function g, and then I define this dual function g sharp like this, that turns out to be submodular. If I write kf to be the total curvature of f and kg to be the total curvature of g sharp, then our theorem says that the approximation ratio of the Sidney decomposition for our problem can be refined to this thing, 2 over 1 plus delta, where delta is this slightly complicated thing. So this approximation ratio is always between 0 and always between 1 and 2. So the delta could be 0, in which case it just get the same as the original result, 2, or delta could be 1, in which case you get an approximation ratio of 1, so an optimal strategy. So that's kind of nice to give a gradient between optimal strategies and 2 approximate strategies. And so we can look at some examples of applying this idea of curvature. So if I take this problem, so no precedence constraints and just weights on jobs, but I have a concave function of completion times, then kg, so the total curvature of G sharp is 0, but the total curvature of F can be calculated like this. I won't maybe go through the details because I want to talk about the other paper as well. But we could get a nice expression for the approximation ratio here. And if I take some particular examples of functions, like this logarithmic function, I guess an approximation ratio in terms of the parameter a in the logarithmic function. And then if I take this exponential function, same thing. I can get the approximation ratio in terms of that parameter r there. Okay, so now let me spend the rest of the talk talking about the second paper. So this is still the min-sum ordering problem, but for a different class of functions, different classes of functions. So when we started working on this paper, I was thinking, well, maybe if we have a result for F submodular and G supermodular, maybe there should be some result for F supermodular and G submodular, some other approximation result. And it didn't quite work out like that, but we actually ended up with, in some sense, a more general theorem than that. So let me just talk about some previous work with submodular F. So if we take the min-sum ordering problem with F submodular and G just being the cardinality function, so I take a subset, and G of that subset is just the number of elements of that subset, then there's a for approximation for that problem in this paper. And then a slightly more general version of that, if I take G to be modular, so the cardinality function is a modular function. If I take a general modular function G, then there's also a for approximation. And I think these two works are in some sense independent, because the later work I don't think was aware of the earlier work. But both of the proofs of these for approximation results were inspired by a very beautiful and mysterious proof, or at least mysterious to me, given by Feiger, Lavache, and Totali for approximation for a problem called min-sum set cover, which may be unfamiliar. And the way this works is, well, to think about the usual form of set cover. So the classic set cover problem is that you have a ground set and a bunch of subsets, and you want to choose a collection of subsets that cover the ground set. So everything in the ground set is in some subset in your cover. And you want to choose a minimal cover, so a minimal number of subsets that cover the ground set. That's set cover. Min-sum set cover is slightly different, because the elements of the ground set are chosen one by one, and each time you choose an element, maybe it's the other way around. Each time so the elements of the subsets are chosen one by one, and every time you choose an element, a subset, then you cover some of the elements of the ground set, and you want to minimize the hitting time of all the elements of the ground set, so that the sum of the hitting times. So and you could think of that as an average. So the average time that the elements of the ground set are hit by the cover, by the elements of the cover. So our result is also inspired by this this proof of this for approximation for min sum set cover, and I'll give you a general idea of how the proof works shortly. So this is our result. Before I give it to you, we need a definition. So an alpha approximate Sidney decomposition. I said what a Sidney decomposition is when you recursively maximize this ratio of f to g. An alpha approximate Sidney decomposition is one where at each step you approximate the maximization, this density maximization problem within a factor of alpha. So the first set we choose in the decomposition doesn't necessarily maximize the ratio of f to g, but it approximates this maximum density within a factor of alpha. So alpha is some number greater than 1. So the result says, suppose f is subadditive. And this is the only assumption we're making on f or g. Apart from the assumptions we always have that f and g are non-decreasing of the empty set as 0. Apart from that, we only assume f is subadditive. G can be anything. Then if we can get an alpha approximate Sidney decomposition, if we can get an alpha approximate Sidney decomposition, then anything consistent with that is a 4 alpha approximation for an optimal chain for the min sum ordering problem. So if we can approximate this density problem of finding an alpha approximate Sidney decomposition, then that gives you a 4 alpha approximation for the original problem. And just to say what I mean by subadditive, so this is a bit like submodularity, but it's a less strict condition. Subadditive just means if I take any disjoint sets, f of their union is at most the sum of f of those two sets. So anything that's submodular is also subadditive, but the implication doesn't work the other way. And this is how the proof works, and I'm just showing you for alpha equals 1. So if I can get an exact Sidney decomposition, then we want to show there's a 4 approximation for the original problem. And the proof is almost identical to this proof min sum set cover. So it works like this. Suppose I have this Sidney decomposition, S0, S1 up to Sk. And then suppose this is an optimal chain, T0 to TL. Then I'm going to rewrite the objective function for the Sidney decomposition, so for my proposed 4 approximation solution, in this way, in this kind of weird way. And I don't have good intuition for this, I'm afraid, but if you substitute this phi I into this sum, then you see that this bit cancels with this bit, and I get just the sum of this and this. And you can show that by rearranging the original sum, it's just algebra to show that it's equal to the sum of these things. Then here's a histogram that represents the objective function written in that weird way. So the width of each bar of the histogram is this sum here, and the height is this phi I. So it's not necessarily increasing or decreasing like the original histogram that I showed you. Then we can also write the histogram for the optimal chain in the usual way, the way that I showed you at the beginning. Then the way the proof works is that I take the histogram of the proposed 4 approximation and I scale it by half in the horizontal and vertical directions. So I shrink it like this. And then I show that it fits into the second histogram. And that that's sufficient to prove that it's a 4 approximation, because when I scale by half in both directions, that means that the total objective function is a quarter the size of the original one. And it's just a few lines to show that by scaling it like this, it fits into this histogram. So the proof is very mysterious to me, but it seems to work out. So first, I'll mention what I mean by known applications is applications of the theorem to prove theorems that are already proved. So the 4 approximation I mentioned before for F supermodular and G, the cardinality function, given by this paper, and then the 4 approximation for F submodular and G modular. It can also be used for something called the expanding search problem, which I'm not going to explain in detail, but it's a search problem defined on a graph. And it doesn't exactly prove this result because this is an 8 approximation. So it proves the part of the result that says if you get a 2 approximation for the density problem, then it implies an 8 approximation for the original problem. And actually, I think since this paper, there are better approximations for the expanding search problem. It also can be used to show a 4 approximation for something called the bipartite OR scheduling problem. And I won't say what that is because I'm going to describe a slightly more general OR scheduling problem and a 4 approximation for that. So what is OR scheduling? Maybe less familiar than the usual form of precedence constrained scheduling. And the way it works is, as with the usual version, you have jobs corresponding to nodes of a DAG, but unlike the usual version where a job can be completed when at least one of its predecessors has been the usual version is a job can be completed when all its predecessors have been processed. In this version, a job can be processed when at least one of its predecessors has been processed. So this turns out to be a harder problem in some sense. So an implication of our result is there's a polynomial time 4 approximation for this problem for minimizing the sum of weighted completion times with OR scheduling, as long as the precedence constraints are in the form of an in-forest, or more generally, a multi-tree. So it's a special case. Let me tell you what these things are. So an in-forest is a DAG where each node has at most one successor. So it's something like this. So if it's connected, then it's an in-tree, but it doesn't have to be connected, so it's an in-forest. So you can see in this picture, every node has at most one successor. And a multi-tree is something where for each node, if I take all its successors, then that's a tree. So that's an out tree. So if I take, for example, this node here, all its successors are these ones. So by all its successors, I mean its successors and the successors of its successors, etc. So all its successors here are, my cursor's disappeared again. There we go. So the successors of this job are this one, and this one, and they form a tree, a subtree. And so an in-forest is an example of a multi-tree because for an in-forest, all the successors of a node just form a path. So a multi-tree is a more general version. So it turns out that if we take a multi-tree, then we can solve the density problem precisely. And it just follows immediately from that and from our theorem before, our general theorem, that you could get a 4 approximation because all you need is that by writing this problem in the form of the min-sum ordering problem, all you need is that F is subadditive, and that's easy to show. G, it doesn't matter what G is, but you just need to show it can be written in the form of the min-sum ordering problem with a subadditive F. Okay, so I'll just end by mentioning some possible future work. So I think if this theorem is going to be of any more use in general, then more work is needed on the density problem. So by the density problem, I mean the problem that you have two set functions. So this is not really a scheduling problem; it's a more general problem of to do with set problems. But if you have two arbitrary set problems, trying to maximize the ratio of those two problems. This is a hard problem in general, but if approximation results could be obtained for that, for some general forms of set functions, then that could be used to get approximations for the min-sum ordering problem for those particular set functions. There's something called the generalized min-sum set cover problem, which is related to the min-sum set cover problem, where unlike with the min-sum set cover problem, where you want to minimize the sum of the hitting times of all the elements of your ground set, in generalized min-sum set cover, each element of the ground set has a kind of hitting requirement. So you need it to be covered by a minimum of k subsets for some k. So if k is 1, it's just min-sum set cover. But it could be arbitrary k. So our theorem implies that if you can solve the density problem for generalized min-sum set cover, that will give you a 4 approximation for the problem. And at the moment, as far as I know, and please correct me if someone knows a better approximation, I think the best known approximation is something like 4.642 from this paper here. Okay, so thank you for your attention, and I'm happy to answer any questions.
So thank you very much, Thomas, for a very interesting talk. I now open the floor for questions. So if you have any question, please unmute yourself and ask away.
May I ask a question?
Yes, definitely.
Okay, Tom, so thank you very much for your talk, which was, as usual, very, very interesting, and you addressed a lot of different results. I have a very simple question because I never heard about these or precedence constraints. So I was wondering, what do we know about that? In particular, is there anything like the Sidney decomposition applying to or precedence constraints as well? Does the concept might it have the same relevance or not?
Yeah, so I don't know a huge amount, and I don't think there is much work on or precedence constraints. I think the expert is my co-author Felix Happach, who I believe has left academia, unfortunately. But I mean, so our result says that at least for these multi-trees, if you take a you can find a Sidney decomposition in polynomial time for multi-trees, and that gives you a 4 approximation. But for general OR scheduling, that would be an interesting open problem whether you can find an approximation for a Sidney decomposition, or whether you can find a precise Sidney decomposition. If you could find a precise one, then our result says that gives you a 4 approximation. Or if you could approximate it by alpha, then our result says that would give you a 4 alpha approximation. I don't know about any result of the form that an optimal schedule must follow a Sidney decomposition. That would be a stronger result that may not be true, and I'd have to think about that.
Thank you.
Okay, are there any other questions? I actually have one technical. I was not sure about the Sidney decomposition and maximum density subsets connection. So are the maximum density subsets like constructed in each step of Sidney decomposition?
Yeah. So you can think of this Sidney decomposition as finding a maximum density subset and then repeating. So it's repeating on all the jobs that you haven't yet chosen. So then finding a maximum density subset of the remaining jobs, and then finding a maximum density subset of those remaining jobs, and so on until you've chosen all the jobs. In practice, at least for the first paper, when you have F submodular and G supermodular, the way of finding the Sidney decomposition is not that you find them in order, but you kind of find them all at once using this parametric search technique. So if you think of the slide where the line was going like this, and you're maximizing G of A minus F of A.
I see. Thank you for the explanation, Mas.
Of course.
So any other questions? So if not, I thank you again for your very nice talk, and I want to just remind every one of you that we will be coming with the seminars in September, and we will keep you posted about the particular date of the first talk. So thank you all for the attendance, and I look forward to seeing you in September. Have a wonderful day and goodbye.
Thank you, Willem.